What's going on, everyone? All right, once again, we are going to dive into the OChem Rockstar approach so we can discover what is possible. Like I said, not what everybody else is telling you, but here in the elite group, discover what you are capable of doing. All right, so we are finally going to dive into, I know you all have been anticipating, what are these three phrases that you keep talking about, Jay? In terms of mechanisms, what are they? Please tell me now. We are going to finally dive in. Here are the three key phrases that will help you with mechanisms, all right? Now, remember we talked about that with reaction questions, what we're going to be doing is your professor's going to wind up giving you everything except the final structure on the right-hand side, and we have to predict that based off of everything we have. We've talked about how we can get super dialed in by using that template. One of the first videos we did, we could find out exactly how to figure out where to look by using the patterns from left to right, top to bottom, and we could zoom in specifically on the atoms like we did right here. We use the periodic table, and we use electronegativity trend. Then what we talked about is when we get into mechanisms, that's going to be, we're going to have everything. We're going to have the left, the things above and or below the reaction area. We're going to have what's on the right. We're going to have everything. But what we have to do is get super dialed in and know how to draw all of our arrows based off of this one reaction where we go nucleophile to electrophile, negative to positive, and we're going to draw our arrows kind of like a Google map, all right? So we've kind of seen this before a couple times where this is what the arrows would look like for the mechanism for this specific reaction right here. And just to throw another terminology in that we're going to get into not this week but next week, this is going to be called an SN2 mechanism. It's a substitution reaction, and it's specifically with a functional group called alkyl halides. All right, I'm going to start dropping in some big terms right now, some big words, but I know it's not going to phase any one of you because you all are dialed in. You know exactly what to look for, and all these crazy words don't even phase you at all, right? It's because you all are dialed in. Now, here we go. Like I said, all organic chemistry reactions have a detailed mechanism, and the reaction mechanism is like a Google map telling you how to go from start to finish. And remember, I initially said there are two key phrases that I want you to keep in mind, but I realized that there are actually three, and I had to update that, and we're going to go over them right now. These are the three key phrases that I want you to keep in mind, in your mind, like seared in your brain when you're doing mechanisms to know what to look for. And here they are, okay? Lone pair to bond. So we've kind of talked about what lone pairs are. Those are if you have an atom and you have just two electrons floating around on there, that's a lone pair. A bond is between two atoms. You can have bond to bond, so one bond can go to another bond, or you can have bond to lone pair. Now you might be saying, well, Jay, not what I thought it was going to be. I don't understand this really. Well, don't worry. Once again, it's not about the words. It's about what we're going to see with our eyes and how we're going to dial it in. I bring these terms in because these terms are going to be a lot easier than the ones you read in your textbook. But it's always dialed in. Remember, if you know where to look, you can solve any problem. We want to get so dialed in with our visual element. I know we all learn differently. I do too. I've got a lot of different ways to learn. But this is going to be a big one right here with your eyes and be able to dial in how to draw it, okay? So what we're going to do is we're going to take what we talked about last time, the top four things you'll see in every reaction. Now, instead of just drawing the arrows like we did last time, we're going to draw the arrows like last time, but I'm going to show you how to use these three key phrases, okay? So let's start with number one, attack. So if we were to take this reaction right here, we already know how to get dialed in and look at these. If you're at this point and you're just still not sure, you can always go back and watch the videos again. Make sure that you understand this one reaction based off of how we can figure that out off of the pluses and the minuses, off of the periodic table, off of the electronegativity trend. Get that so dialed in to where it's automatic when you know where to look and you know why it's going to go, which way it's going to go. So we said that it's going to go nucleophile to electrophile, N nucleophile, N negative, negative to positive. So we'll draw it in here again. Negative to positive ultimately gets us to the product. So in this case, once again, we're always trying to identify which way is it going to go. Is the functional group in green going to attack the reagent in blue? Or is the reagent in blue going to attack the functional group in green? And we know how to get this dialed in. It's all about finding the charges. And we do that once again with the periodic table. And we do that with the electronegativity trend, okay? So in this case, if we were to get dialed in, I'm going to walk you through this anyway because the more times you see this, even if you're like, oh my gosh, Jay, I think I got this, you probably don't have to walk me through it. I'm going to do it anyway because I want it to be second nature. I want it to be when somebody asks you a question, bam, you know how to say it. If somebody needs help, bam, you know how to help them. You just are so dialed in that literally, even at this stage, you could teach the class. No, I haven't lost my mind. I know you're already dialed in that you could start teaching people exactly how to do this, all right? Cool. Now, once again, what we do is we take our functional group. We use our electronegativity trend. Remember, every functional group has two atoms. One of them is typically carbon. The other one's more electronegative. So we can drop in our partial negative, partial positive. We already know our CN is negative. We got that from the reagent. Our carbon is partially positive. So we're going to draw our arrows then. So in this case, check this out. When I do my Cn minus, remember, anytime you see a negative charge, that means there has to be a lone pair, 2 electrons on that atom. Because when there's a negative charge, there has to be electrons that we can use as like a plug. We're going to plug it in somewhere. So when you see a negative, I'm going to draw it, but your professor may just give you a negative charge. But I need you to remember, because I know you're going to be dialed in, you're in this elite group, you're going to remember that there are 2 electrons there. So you don't have to draw them with the mechanism. I'm going to do it because I want you to see them, okay? Now we know what you can do here is you can start your arrow either at your lone pairs or your minus, but check this out, and now I filled in all the lone pairs. Remember when we saw the halogens in that group 7? All of them have a total of 3 sets of lone pairs. So the reason I'm putting everything on here, all the lone pairs, is because when we do this mechanism, I want you to see where everything's going. Now when you get dialed in, and on most of your exams, you're not going to see all these dots. You're not going to see all these lone pairs. Professors, a lot of times, are not going to put them in. But I want you to be able to see them so you can see how this is breaking apart, how we're going to form bonds and break bonds, so then later on you don't need to draw them. It's dialed in. You know exactly what to do. So check this out. The first thing that happens is we're going to go lone pair to bond. How does that work? Well, it kind of makes sense, right? The phrase is kind of self-explanatory. We have a lone pair. We're going to use that lone pair, and we're going to create a bond. All right? Lone pair to bond. So it's like a negative charge is a lone pair. We're going to use that lone pair to form a bond. The second thing is if we do that, we have to maintain our 4 bonds to carbon. If I just form a bond, that's going to give me 5 bonds to carbon. And if you're not sure how I got the 5 bonds, go ahead and rewatch some of the videos. Make sure you see how I know there are 4 bonds to that carbon with that bromine. Because remember, we don't draw hydrogens. So we have to count the number of lines, but some of them are quote unquote hidden, okay? If I just draw the red line, that'll give me 5 bonds to carbon. So something has to get out of the way. Why is the function group there? To get out of the way. The function group, like I said, is the part of the molecule that allows you to do something. And the main reason it's there is so it can break, open up a space so something comes in. So either it comes in, attacks, and then it falls off, or you'll find out sometimes it falls off first, then something comes in, attacks, okay? But we need that function group there. It kind of opens up a space for us. And then it's going to be bond to lone pair. Now let's go ahead and look at the colors here. Do you see how now I took my lone pair, and now there's a red line between my CN and my carbon in my chain? And you see how now on my bromine on the right-hand side, there's an extra 2 electrons that are blue? That was the bond. See, the bond now turned into a lone pair. If I take a lone pair and I form a bond, it's now not 2 electrons by itself. It's formed a bond. Now, you might be saying, well, Jay, your arrow's below the bromine. Why did you draw your carbon CN up? The reason is because when we draw these, you're going to find out that what you try to do is you always draw lines. If you have a mountain, you always draw it off the top. Or if you have a valley, you draw it straight down. When you have a mountain like this, you don't draw it down because the bond angle is super weird that way. So you're always going to typically draw this way. So although I'm drawing my arrow down below, I'm still going to try to draw my bonds as easy as I can, or the way that they typically see in the class, okay, in the textbook. So you can see I've got lone pair to bond, bond to lone pair. That's another way you could say it is forming bond and breaking bond, okay? So now if we were to look at this without the colors, this is what it would look like. You would just draw your arrows and you can see lone pair to bond, bond to lone pair, okay? Let's take another one, okay? So if we look at this one right here, once again, we would take this, we would get dialed in left to right, top to bottom, periodic table, electronegativity trend, and we'd be able to find these are the 2 atoms that we really want to pay attention to, okay? Now, the thing is sometimes you're going to find out when we get into alkyl halides. Right now, we don't have to really pay attention to how we're doing this. Just trust me on this part. I'm hoping that you can trust me at this point in time since we've gone through this, and it should be clicking, light bulbs going off, and aha moments. But just trust me that sometimes we're not going to attack a carbon. We're actually going to grab a hydrogen. So this would be considered a what? A deprotonation. Now, when we deprotonate, sometime we're going to need another phrase, and you're going to see that in a minute. But once again, it's all about getting dialed in. I'm going to show you once we get into these function groups how to know it's right there. But now you can see it's still going to be the same thing. Where's my minus and where's my plus? So in this case, my oxygen is partially negative. We know hydrogens are typically positive, so I'm going to go minus to plus. So let's go ahead and check this out right here. Once again, I'm going to draw all my lone pairs, all my electrons. I'm going to color code my bonds so we can see this as we go through. Now check this out. Once again, we're going to start this lone pair to bond. This is a deprotonation, even though it still could be considered an attack, correct? Because we're attacking the hydrogen, but we're going to go lone pair to bond, which means I'm going to take those red electrons and I'm going to form a bond between my hydrogen. When I attack a hydrogen, remember we saw if I form a bond, I have to what? I have to break a bond. So what's going to happen in this one is, I just realized we're going to do this second because this is another phrase. I want you to see that in this whole mechanism, we're going to do lone pair to bond and then bond to lone pair. You might be saying, Jay, how in the world is that going to happen? Well, there's another phrase that we already talked about that's going to have to be in here, which is called bond to bond. So in order to get this whole thing to work, the red electrons are going to come in and grab the green hydrogen. When I just grab the green hydrogen, the bond is still there. Now watch my finger. The bond, oh, it's going to be this way for you. The bond is here. What's going to happen is that bond is now going to swing up like this. The electrons are going to swing and form a bond. When it does that, the electrons are going to kick the bromine out. So we go lone pair to bond to bond, and then bond to lone pair. And it's ultimately going to give us this structure right here, color coded. So once again, you can take a screenshot of this. Just take the time to make sure that all the colors make sense. But that's going to be a sequence: lone pair to bond, bond to bond, and then bond to lone pair. Okay. Now, what I want to show you is I want to do step by step. So this is a lone pair to bond. What does that look like? That's that structure right there. So I form, look at that. Watch, my O is going to grab my H. Do you see that on the right-hand side? Now look on the left-hand side, my bond's still there. I can't just have a bond without an atom. That doesn't make sense. So what's going to happen is that bond is going to swing down like a door on a hinge. Bam. And when it does that, in order to maintain the correct number of bonds to carbon, which is what? 1, 2, 3, 4. It's going to kick the bromine out because the bromine is there, the leaving group, the functional group is there to get out of the way. So it's going to kick out. So now we can see here that there's our bond to bond in green, the first one on the right-hand side of the arrow. Then we've got lone pair to bond, which is our red line. And then we have bond to lone pair. Now we've got the blue dots on our bromine. So you see how all this is about is moving 2 electrons. We take 2 red electrons and we grab an H. We take 2 green electrons and we swing them down to form a bond. And then we take 2 blue electrons and we push them up on the bromine. 2 electrons over and over and over again. 2 things for every 1 reaction, nucleophile electrophile. This number 2 is very, very important in organic chemistry. All right? Now, we've done this, so now let's go ahead and look at, that was attack, let's go ahead and look at deprotonate. So if we look at this right here, we can wind up doing the same thing. We can get dialed in. We've already talked about it, so we know exactly where to look. We can get dialed into the specific atoms, and then we can go ahead and draw our arrows, and we know that it's either going to be from green to blue or blue to green, but we know it's going to be blue to green because oxygen is partially negative and hydrogen is partially positive. So if we draw our arrows, it's going to be basically, I'm not drawing the lone pairs this time, okay? So I'm just going to draw it from the negative, but I know you know there are 2 electrons. This is completely fine to draw an arrow from a negative. You don't have to draw it from the 2 dots unless your professor says draw all the electrons. You'll also notice I'm not drawing all the lone pairs of electrons around oxygen. But you can just do this. So this is going to be basically lone pair to bond. And if we form a bond, we have to break a bond. Bond to lone pair. And what it would look like on the backside is this, that now our O minus is now grabbed an H, so we have a new bond between that O and H, and we've broken the bond between our O and H off of our carbon chain with our kink structure, and now it's an O minus. So you'll see that this minus has gone from one oxygen to another based on how we go from lone pair to bond, bond to lone pair. All right? It's pretty simple, right? And so now let's look at the next one, leave. Let's see what happens here. So if I took this structure right here, you can kind of see where this is going. We've already seen when I've done lone pair to bond, bond to lone pair, the bond to lone pair was the leaving. We've already talked about that. So now when we're dialed in here, once again, this is a no-brainer. There's only 2 things to really work with here. So we've got these 2 right here. We know it's our functional group. We can go ahead and draw arrows, and this is literally just bond to lone pair. We're going to dump them up on our bromine, which will give us one structure that's positively charged, like we talked about in the last video. One of them is negative, and it makes sense the bromine's negative. Here's 2 reasons why it's easy to figure this out. We know that bromine is more electronegative than carbon, so if we're going to do a negative charge, it's going to be on the bromine. Second, look at your arrows. Have you noticed that your arrows are always showing you where the electrons are going? When you have a lone pair, 2 bond, the electrons, the arrow is showing you I'm going to take the 2 electrons and I'm going to plug it in. When you do this, it's saying take the bond, which is 2 electrons, and shove them up on the bromine, okay? So you're either going to take 2 electrons and plug it in, or you're going to take 2 electrons and dump it on an atom, okay? Or you can form another bond. You see? I mean, it's literally like the same pattern over again. Lone pair to bond, bond to bond, bond to lone pair. All right, now if we wanted to, this obviously is not the way the reaction works, but let's just imagine we went backwards, we could do the same thing. So if I took this and did the reverse reaction, I would go minus to plus, which is going to be lone pair to bond. And now you can see, just generally looking at this without all the colors, just the arrows to get an idea, you can now look at this to see the top one is lone pair to bond, bond to lone pair. The middle one is lone pair to bond, bond to lone pair. And the bottom one is just bond to lone pair. So attack, deprotonate, leave if you want more specific terminology. And that's literally all there is to these mechanisms, all right? Do you see how much easier those phrases are? Like when you read it in the textbook, it's going to be incredibly complicated, but these phrases like streamline the whole thing where it works on every single reaction, all right? Now, with that, once again, it's been an amazing day, but the thing is with this, I absolutely love coming on here as always. I'm getting tripped up because I just get so excited. Sometimes I lose my words, but the thing is I'm so excited that you're here. And with that, I hope you all have an amazing day. And until next time, I hope you all have a good one.